I have a few things I want to say. So the first thing is I want to thank everyone that has subscribed to the channel, that likes the videos, and that leaves very thoughtful comments. This channel has gotten a lot of attention in the last 9 days, more than I'm used to, because we're almost at 1,000 subscribers. I have a second channel which does have 1,000 subscribers, but it took me like a year and a half to get there. So to see 900 subs in like 9 days is kind of overwhelming. And I want to thank you for showing your support and interest in these videos. I'm glad you find these interesting, otherwise I'm just talking into the ether. And for those that have left really thoughtful comments and have asked questions, I do read your comments and I do want to respond to them. And I do respond to some of them, but I can't find the time necessary to articulate the best response and give you those responses that I want to give you. So please don't think I'm ignoring you, because I'm not. But I do read them, and I'll try and think about them when I make these new videos. So that was the first thing. The second thing is that I want to do a series of videos about concepts in measure theory. So I made this list last night, and there's some more on the back, but you can see here that we have a bunch of things. So it looks like 35 topics is where I decided to stop. And I'll try and go in this order. It's a very natural order, I think. I tried to mimic textbooks that I've read. The Royden book is probably the thing I looked at the most when I made this list, but I don't like everything he does, but the Royden book is my favorite, so it's the one I like to follow. And if you see something on here and you want me to mention something specifically, like with, I don't know, what would be a good one? Pointwise convergence versus uniform convergence. If there's something specific that you want to see, maybe leave a comment and I'll think about it. I'm not promising that I can fit all of it into the video, because I think that will be difficult if there's a lot of requests. But the idea is that I'm not trying to lecture. I think there are plenty of videos already on YouTube of lectures in measure theory, lectures in functional analysis, lectures in, I don't know, group theory, you name it. There's probably there's probably enough videos like that already, and it's not really what I want to do. What I want to do is essentially provide a review session for these concepts for grad students that are already taking these classes and have the notes in front of them, or have taken this class before but they don't really remember much. So with the first video, it'll be about Lebesgue outer measure. I want to talk about it in a very informal way, because I think that will take away the intimidation factor. Because when you're in a class and you go through all of this stuff and you look at their proofs and blah 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 and all those terrible things, it's very intimidating, and without proper context I think it's kind of lost, and I think that's a shame. So my intention is to try and break things down in the most simple way possible with tons of pictures and examples. And I do want to end every video with a problem that's very simple to do. And even if you can't do it, you can find the answer on the internet. So I think that would be a very productive use of time. So remember, and if I end up making every one of these videos, and you watch them all and you do all the problems that I give you, remember still, it's imperative to do more problems, because that's how you learn things. So where can you find such problems? I mean, textbooks will have problems in the back of it, but a lot of the times they don't have solutions, so you can't even really check your answer. And finding an answer on the internet can be challenging at times, because there's not a whole lot of resources out there. But I can only do so much. I'll try and do what I can do to help anyone that wants help in measure theory. And I decided for some reason to stop with Hausdorff measure and dimension. And that's mostly because my thesis covered Hausdorff measure and dimension of certain Cantor sets. So I thought it would be a nice little bow to wrap on the end of the lecture series. Well, not lecture series. It's not supposed to be a lecture. Video series. And when will I start this? That's a good question. I haven't really picked a date yet. So maybe it's dangerous to show you all this, before I actually plan out everything and then start recording those video lectures. But it won't be too long. It'll be in the near future. And then once I start it, I'm going to go through every video until I get to the end. But there's still a lot of things I want to talk about before I start this series, because I don't want to start with the first video and then talk about something that happened at university that day, and then maybe talk about teaching, my calculus course, and then finally I get back to sigma algebras. I kind of want to do it all in one order. So it's whenever is most convenient where I can start this and just go through everything. So that's what I plan for the future. Now, for the rest of this video, I thought I would talk about algebra and analysis, because those are the two topics that are typically covered in a pure mathematics PhD program. Now, applied math has their own thing, so I'll list the applied math stuff. Applied math will talk about numerical analysis, just so everything's up on the board in case you want to compare the two. And I'm not going to talk too much about applied math because I'm not in applied math and I don't really have the background. But numerical analysis is one topic. The next one is probability theory, which is the class I'm taking this semester and studying for my test. It's essentially measure theory for applied math people. Numerical analysis, I don't really know what it is. I know there's matrices and linear algebra in it, and I do like linear algebra, but I don't like matrices. The next one is statistics. I think that runs next year, and I want to take it. And then the fourth one is methods, which is short for methods of applied math. Hard to write with one hand. Well, everyone writes with one hand, but I can't steady my paper. There. Methods of applied mathematics. And the way it works in applied math is that you have 4 options here, and you take 2 qualifying exams, and you get to pick. And they run in sequence. So this semester, these 2 are running together. And then next year, these 2 will run together. So it does kind of suck that if you want to take this one and then this one, then it takes 2 years to do it. You can't just do it one and done. But that's the way they've chosen to do it. Whereas in pure math, there's 2 options and only 2 options, and you got to take both of them. So you have group theory, ring theory, field theory. The first semester, you start with group theory, and groups are they're not the most fundamental structures, but every textbook starts with groups because they're the most simple objects that are worth studying, I guess. Or at least that's what, I guess, algebra authors deem as the most fundamental. Now, what groups are, essentially, they're sets that have some sort of operation defined on them, and they're closed under that operation, and they satisfy 3 properties. The properties are associativity, existence of inverses, and the identity element. And so the whole first semester is about groups and different properties you can derive of groups. And then in the second semester, you have ring theory, where you impose another operation on that group structure, and it has to satisfy a set of axioms. I'm not going to go through the definition of a ring, but the most basic example I can give you of a ring is the ring of integers. If you add any 2 integers together, you get an integer. If you multiply any 2 integers together, you get an integer. So those are the 2 operations. And there's other things too. Those aren't the only two things you need to worry about with rings. And there's actually, I think, some sort of debate about whether or not a ring needs a unit. And some textbooks, I think, say yes, it does. Other textbooks says no, it doesn't. But we'll leave that for the algebraists. I won't comment on it too much. And then after ring theory, you have field theory, where field theory throws in the existence of a multiplicative identity. So, for example, the ring theory. My gosh. Real numbers. Real numbers are a field. Every non-zero element has an inverse, multiplicative inverse. And then you study that. And for some people, you know, they'll find field theory the most difficult. For me personally, I thought group theory was the most difficult for whatever reason. I just didn't. I think it's because the structures are so simple, you have more freedom to play with. Or at least that's the way my brain worked. And because of that, you could ask really complicated, weird questions. And for that reason, group theory kind of turns me off. Ring theory I like because, well, it's either, you get one of two options. Either the ring theory problem, I heard one grad student that is getting his PhD in algebra. He said that the ring theory problems for the qual fall into one of two categories. Either it's the easiest problem on the test or it's the hardest problem on the test. There's no intermediary step. I'm not sure if I agree with that, but I do think that a lot of the ring theory problems that we were given were pretty easy. So for those reasons, I like ring theory. And then field theory, I probably like the most, believe it or not. Some people say that field theory and Galois theory, which is basically a part of field theory, is the most challenging of the three. But I didn't find it that challenging, to be honest with you. Maybe that's just me. Let me know what you think. So if I were to rank these in terms of difficulty, I probably would say ring theory is probably the easiest, but field theory is not much harder. And then group theory I just didn't like because the problems can be weird. But, you know, it's dependent upon the person, because I know another guy getting his PhD in algebra, and he thought group theory was the easiest. So, you know, it just goes to show you that different people have different opinions, turns out. All right, so then what does that make analysis? Analysis is kind of, it depends on the course and the textbook. But a lot of places will start with measure theory. There's almost always a semester dedicated to measure theory. Measure theory is all about, you know, describing the sizes of sets and how you can do it. Another thing that people will talk about in analysis at the graduate level will be like metric and topological spaces. And depending on how the instructor wants to go, they may do measure theory first and then metric and topological spaces, or vice versa. I believe the Royden book starts with measure theory and goes here, but the Kolmogorov book starts here and goes here. So they're kind of, I mean, they are interrelated, but you do get some freedom with how you want to present the material. And there's also probably a section dedicated to functional analysis, which usually follows this guy. So this guy will come first, and then maybe this guy will come second. And the thing about analysis that makes it different from algebra is that in algebra, they pretty much follow this pattern. It's group, ring, field, because groups are the most basic. Then you make it a little more complicated with rings, and then you throw in another thing with field to make it a field. And with analysis, it's kind of, the author can kind of pick and choose topics what they want to talk about, but usually any given analysis book will have probably some combination of these three things. And sometimes they may remove it altogether. So let me give you an example. Like the Stein-Shikarchi book. This book starts with measure theory. So it starts with measure theory, goes into integration. This is really just more measure theory. Differentiation, which they'll talk about it in the context of measurability. But then he goes into Hilbert spaces, which kind of fits more into functional analysis. And then he decides to come back and talk about abstract measure spaces and abstract integration, where they take like the Lebesgue integral and make it even more general, which sounds even scarier. And then he decides to end on Hausdorff measure and fractals. So again, he has some liberty with what he wants to talk about. And then if we look at another, I'm going to skip the Rudin book here. I don't want to talk about it. But if we look at this book, Measure and Integral, this is what I used in my first semester. And you can see on the cover it says, An Introduction to Real Analysis. And yet there's not like... okay, we'll just go through it. Chapter 1 are the preliminaries. So this is kind of the stuff that he's expecting you to be familiar with already, which includes like the ideas of metric spaces and topological spaces. And then he decides to talk about functions of bounded variation. We skipped this chapter when I went through this course, and we went straight to chapter 3 and 4, which was about the Lebesgue measure and Lebesgue measurable functions, which are pretty typical in a measure theory course to go through it that way. Oh, the Lebesgue integral comes next, Fubini's theorem, which is like repeated integration. And then he talks about derivatives with respect to measures. And then he decides to go into LP classes, which is kind of in the world of functional analysis, like what the Stein book did. This book's kind of weird. He talks about a lot of different things. Abstract integration, abstract measures. So here he also talks about the Fourier transform, harmonic analysis. And then chapter 14 and 15 are weird. I don't really know of any other measure theory book that talks about the stuff that they talk about in chapter 14 and 15. Which is why I don't really recommend this book for beginners. If you've had measure theory before, then I would say check it out. And then I guess I'll show you the Kolmogorov book. Because each of these books could be used in a course in analysis, graduate level analysis. And they all do it differently. So the first chapter is just set theory, which is something that you would see like at the undergrad level. And you can see that there's a big section dedicated to it. And then he goes into metric spaces, finishes up there. And then he goes into topological spaces. So a good chunk of the book is dedicated to just those two topics. Haven't even mentioned measure yet. And then he goes into linear spaces, which feeds into functional analysis. And then down here you have linear functionals. Functional analysis, by the way, is sort of like the love child of real analysis and linear algebra. So if you like both of those topics, then you'll like functional analysis. And then you can see here, chapter 6 is about linear operators. So all of that is like metric spaces, topological spaces, and then some functional analysis. No mention at all of measure. And it's not until chapter 7 where he talks about measure. So, and he progresses in the normal way. Measure, integration, differentiation. It is kind of weird to see that in a lot of these books, they start with the integral, and then they go into the derivative. But if you've taken calculus, then you know you start with the derivative, and then you go into the integral. So I thought that was kind of a neat observation. And they end the book on integration and talk about weird measures, I think. And it's been a while since I read chapter 10, or this book in general. I spent more time with the first 6 chapters than 7, 8, 9, and 10, because I don't really like the way this book does measure. I prefer I prefer Royden's book the most. So anyway, that is the long short of it. Try and get this back in its stack. It'll bug me if it's not. Maybe your school does it differently, in which case that's fine. Every school kind of has their own thing. But you saw my course outline from a video from a few days ago, so you can see just the way that it makes sense to me, the way I would progress through it. But those, I think, are the big topics that you'll see most common in an algebra and an analysis course. And to be honest, I've taken basically algebra and analysis twice, once at the master's level and again at the PhD level. And I still sit in on the classes just to like jog my memory and refresh my skills. But I forgot where I was going with this. My brain is fried. I've done too much analysis, to be honest with you. But it's a skill that you need to practice every day in order to keep up with it, because if I want to pass this qualifying exam, I need to stay on it and do more problems. Anyway, so that's what's been on my mind recently. Let me know what you think of the list. Let me know what you think of these courses. Let me know how your classes are different from these two. And if you have suggestions, I'm all ears. Thank you again for the subscriptions and the kind comments. I really do appreciate it. Thank you.